So the idea of Cauchy sequences is fundamental in mathematical analysis, and it's super important, and it has important generalization to metric spaces. Basically, the only thing that we need in order to define a Cauchy sequence is a way of measuring distances, that is, a metric. Whenever we have a way of measuring distances between elements of the set, we can define the notion of a Cauchy sequence, because a sequence is just a function from the natural numbers to the set, and then we have a way of measuring distances between elements of the set. So it's actually the distances between elements of the sequence, and therefore if the distance between faraway elements can be made as small as we please, this would be a Cauchy sequence. So the precise definition would be the following one. So let's see the precise definition and generalization to metric spaces. So let X and D be a metric space, where X is a set and D is a metric, and let An be a sequence on X, basically just a function from natural numbers to X. Then we say that An is a Cauchy sequence if for every epsilon that is greater than 0, we can find the natural number n of epsilon such that for every n and m that are greater than n of epsilon, holds that the distance between An and Am is smaller than epsilon. And to recover the old definition that we've already seen, we just replace for the real numbers, we just replace this metric D by the absolute value of An minus Am. It's just one way, possible way of measuring distances on the real line. Okay, so so just in the case of the real numbers, Cauchy sequences are the perfect tool to check if there are holes in the space, because whenever we have a Cauchy sequence that is not convergent, it means that the limit of this sequence is missing, and as a result the space contains a hole. So this motivates actually the following very important definition for completeness of metric spaces. This is the notion of completeness. So a metric space X is said to be complete if and only if every Cauchy sequence converges to a point of X. And we've actually proved that the real line, the set of real numbers with the metric dxy, which gives the distance is just the absolute value of x minus y, with this metric the real numbers form a complete metric space, and this actually stems from the completeness axiom. So now let us see a few generalization of Cauchy sequences. So for example, let us see how a Cauchy sequence would look for the plane. So suppose that we have the plane, and we have the standard distance function of measuring distance between points. Basically, this is the Euclidean distance. So if this point is x1, y1, and this point is x2, y2, then the length of this side would be x2 minus x1 in the absolute value. The way I drew it assumes that x2 is bigger than x1 and y2 is bigger than y1, but the absolute values here can cover all the cases, right? And basically the distance, this is just the Euclidean distance that says that the length of the hypotenuse squared is this squared plus that squared. This is just the Pythagoras theorem. This is the natural way that we're used to measuring distances in the plane. Okay, and so now let's see what properties does this metric have. First of all, we need to really prove that this is a metric. So note first that y2 minus y1 squared is a positive expression, and therefore if I were to eliminate this from here, this will make the expression as a whole smaller. So this means that this expression is greater or equal than that expression. And the square root of something squared by definition, almost by definition, is just the absolute value of the expression. It's just by the property of the square root. So this is just the absolute value. And similarly, we can argue that y2 minus y1 is smaller than that, which implies that this square root is bigger than the maximal of the two. And this makes a lot of sense, because this is exactly like saying that in a right-angled triangle, the hypotenuse is the longest side, so it is longer than the maximal of the two other sides. And on the other hand, we also have this part of the inequality, which is exactly the triangle inequality. Basically, this to prove that this is a metric, we would need to prove this inequality, but it exactly says that the length of the hypotenuse, or for that matter of any side, is smaller than the sum of the lengths of the two other sides. So the length of this side is this, and the length of this side is this, and therefore the sum of those lengths is longer than the hypotenuse. Okay, and if we were to prove this inequality, so how would we do it? We were to square this expression, and we'll have what's inside, and if we square this expression, then we'll have this squared, which will correspond to this, and we'll have this squared, which will correspond to that. and we will have twice the product of those two. Those two are positive expressions, so we will have some positive addition, and that's the way to prove this inequality that we have here. Okay, so this means that now we can ask the question how Cauchy sequences in the plane would look like. All right, so we have the plane, and we have the way of measuring distances in the plane. Okay, and so let Pn be a sequence of points in the plane now. So of course we can decompose Pn into two sequences. Basically, it's just the components, the sequence in the components, the x component and the y component. We get two real sequences, and our guess would be that this sequence Pn is a Cauchy sequence in R2 if and only if xn and yn are Cauchy sequences in R. And since R is complete, xn and yn must converge to some point. Xn would converge to some x, and yn would converge to some y. And as a result, this sequence of points Pn would converge in this metric to the point xy. So let's see this written rigorously. So if Pn is a Cauchy sequence, then for every epsilon greater than 0, we can find n of epsilon such that for every n and m that are greater than n of epsilon, we have that this distance is smaller than epsilon. This is the definition of what it means to be a Cauchy sequence. But on the other hand, we have proved this inequality. And this exactly shows that xn is a Cauchy sequence, because here, for every epsilon, we can find this n of epsilon such that for all n and m that are greater than n of epsilon, this is smaller than epsilon. Right? And similarly, what we have the same for the sequence of the y's. And therefore, we have proved that if Pn is a Cauchy sequence in R2, then those are Cauchy sequences in R. And we can actually show that this works both ways. So we showed only the the if direction. So if Pn is a Cauchy sequence, then those two are Cauchy sequences. But if those two are Cauchy sequences, then basically using this inequality, right, we can show that if we have here those are two, using this inequality, we can show that in the x, if we have a Cauchy sequence, and in the y, then we can make this to be smaller than epsilon half, and this would be smaller than epsilon half, and this will be smaller than epsilon. So if in the x components we have Cauchy sequence, if those two are Cauchy sequences, then so is this sequence Pn. Okay, and so what it means that now is that xn is a real Cauchy sequence, and this is a real Cauchy sequence. And as a result, since R is complete, they both converge. It converges to some point x, and this converges to some point y. And as a result, we have this point P. And in this metric, this distance will be as small as we please. So this means exactly that according to the definition of convergence with respect to this metric, that the sequence of points Pn converges to P. And this actually proves that R2 is complete, right? So basically, we have showed that that a sequence in R2 converges if and only if it is a Cauchy sequence, because every convergent sequence is a Cauchy sequence. And here we've proved the converse. We've taken a Cauchy sequence and showed that it converges. So we have showed that R2 is a complete metric space. And the same method, I will leave it as an exercise. The same method could be used to prove that Rn, basically the collection of n tuples of real numbers, is also a complete metric space with the corresponding metric. Here we'll have just the sum of n components and the square root of that. I hope that this was clear enough. And now we're going to see how Cauchy sequences in the plane converge and how they behave, just small visualization. So now what I've created here is the sequence. So basically it would converge to the point 4, 5. And what you see here is that cosine of j over j is just an index that I used here for the sequence. This would tend to 0 and this would tend to 0, but basically those points are located on a circle around, every point is located on a circle around the point 4, 5 with radius 1 over j. So if we were to zoom out now and see how those points behave, right, let me draw the circles here. So we have two circles. So here's the point 4, 5, and this point for j equals 1 is on a circle of radius 1. And the second point is on a circle of radius 1/2, and the third point, as we will add more points, will be on the radius of 1/3. So if we now gradually increase the amount of points, maybe I will reduce it to, I don't know, just to make a smaller step, right? Just fewer points here. So yeah, so we can see gradually. So the idea is that we see here that the distance of each point, basically because of the cosine of the angle and the sine of the angle, we see that this sequence also kind of spirals inwards beautifully here. But the main point is that it's just getting closer, right? The nth point in the sequence has distance 1 over n from the limit, right? And so let us just see how beautifully we have this nested sequence of circles. And basically, for every index that is greater than, for example, this index, here we'll see that all the elements after that are going to be in this inner circle, right? And so this is how a typical, almost typical convergence in R2 would look like. Just wanted to visualize this. So the distance of the points from the limit is decreasing, and this is just one way to visualize how this particular sequence converges to the limit.